So on to lecture 5. Today we're going to look at mainly order of operations, and this is going to be where we look at some keywords such as the opposite. A lot of times we have a preconceived notion of what an opposite means, but the opposite of a number reverses its sign. It's not always negative, it's not always minus, but it's a reverser. So if you have a negative number and then you put the dash in front of it, it's the opposite of negative, becomes positive. If you have a positive number and you put the dash in front of it, remember that will make it into now negative. So that's what the opposite does. The reciprocal of a number opposite is changing the sign or direction of a number. The reciprocal of a number, which needs to be written as a fraction, switches the numerator and the denominator to create a new number, unless the number is already 1 or -1. And it just takes the reversing effect. These are both kind of ways of reversing, right? Opposite seems like reversing, reciprocal can also seem like it's reversing. But the opposite is what reverses adding or subtracting is to use the opposite value. If you have a positive number, add the negative number of the same magnitude, and you'll get yourself to 0. With the reciprocal, if you multiply a number by its reciprocal, it gets back to 1, not 0. It doesn't make it into 0, because what we do is when we apply an opposite to adding, we get to the neutral value for adding, which is 0. When we apply a reciprocal with multiplication, we get to the neutral value for multiplication, which is 1. So what we can do is kind of eliminate the effect of a number by using its opposite when we're dealing with any kind of addition, and its reciprocal if we're dealing with any kind of multiplication. So let's find the opposite and reciprocal of these numbers, and we'll put them under the term, the names as far as terms go. Okay, what I'm going to do is I'm going to push here a -3. I want the opposite of -3. I don't want it to be negative anymore, but I do still want it to be 3. Okay, the reciprocal of -3, which to me is a -3/1, right? That makes it so I can work with the reciprocal. Now, I still want it to be negative, but I want the 3 on the denominator and I want the 1 in the numerator. I'm not done yet because this started negative. The reciprocal will also be negative. Now, many people will say, oh, look, there you have -3/1, so the reciprocal clearly must have to be 1 over -3. It doesn't have to be, it can be, but what we have to have is the 1 in the numerator, the 3 in the denominator, and the number must be negative. So you can do this, or you can have the 1 in the numerator be negative, or you can have a negative sitting in front, right? 1 over 3. It's negative in each case, because the single negative sign is an odd number of negatives and will make it result in a negative value. The one I most favor is this one, because you don't have to worry about misusing the one that's out in front, as some students have trouble with, and you don't make it seem like you're sneaking around saying, here's my fraction, it's 1 over, and then like, ha ha ha, the cruel guy twirling his mustache, -3, and like you thought it was comfortable, at least it's a fraction, but at least there's no negatives, and then bam, you get hit with that right there. So I do tend to put a negative if I have one in the numerator, by choice, not by absolute demand. Let's try another one. 2/9 begins as 2 over 9, so it's already a fraction. If you want the opposite of that, which is currently looking positive, then the opposite of it would be negative, and that's the number that add to this to make 0, add that to that, you get 0. You get the neutralizer, right? Actually formally called the identity of what happens when you add. And now we want to take 2/9 and we want to get the reciprocal. We'll go straight to it. Put the 9 in the numerator and the 2 in the denominator. No negatives in sight, so no worries about that. Like I said, when you add two opposites, you get 0, which is the neutral value for adding. When you multiply two reciprocals, you get 1, which is the neutral value for multiplying. So they have their purposes, and they have their ways of neutralizing a number that we already have. How about -1 2/5? Now that could also be when I take the 1 times 5, getting me 5 new pieces plus the 2 old pieces, 7/5. But it's been negative the whole time, so I might even make my negative go up on my 7. You can put it in front, you put it on the 5, it's up to you. When you want the opposite of -7/5, you want to make it +7/5. It could still be +1 2/5, but that's also acceptable. It's definitely become positive, no longer a negative value. Having this thing as -7/5 puts me in a position to make sure that now the 5 is in the numerator and the 7 is in the denominator, and it must be negative. So it could be this, or it could be -5/7, or it could be the opposite of 5/7. They each have a single dash functioning as a negative sign. I like the middle one, but I will mark it right, so we'll connect math. We have the other formats of it. So that's what's going on when we're looking at terms such as, vocab terms that we look at for things like reciprocal and opposite. So now we're going to go on to the next part of what's going to be working with us for order of operations. We're going to need to understand how this thing called exponents, some people call them powers interchangeably. It's okay to call them powers for some of the work we're doing here, but when you get to higher levels, even at the end of at Norwalk, our Math 136 intermediate algebra, it's not completely perfect to always refer to any small number sitting up there behind its base as the power. That's an exponent that's sitting there. But anyway, the base, spelled with B-A-S-E, is a repeatedly used multiplier. In the same term, it tends to be repeatedly used. It could be used only once. Strangely, it could even be used 0 times, which means not at all. Weird, but okay. But mostly the base is what we think of when we have a power or an exponent that is something other than 1. And then we have the exponent get to work on how strongly are we using it. The exponent some call it a power. So I'll say power. Remember though that I'm not saying power is what you always use. Power will get us through a lot of what we do here, using power and exponent interchangeably, but keep an open mind that when you really get into exponents in a higher level, that power has a specific use. Is a small, elevated number just after its base. That tells how strongly to use the base, that base, as a multiplier. It wouldn't make sense for me to write the whole explanation I'm about to give right now and then later throw some numbers up on the board. That'll happen shortly, but I want to tell you, the key to determining what you're taking the power of is what is sitting correctly sitting to the left of your power. It's down a little bit because the power is elevated for where it's located, and what sits right in front of it tells you what you're taking a power of. If when you look over there for where your base is, the thing you see is a pair of parentheses, you get everything that's in those parentheses that many times. If you don't see parentheses, you only have the item that sits right in front of your power as your base. So try and keep that in mind, that if you see parentheses, all of those are there according to the power, and if there's no parentheses, only the immediately directly to the left in front of it, whatever it is, whether it's a number or a letter, is what you have the power affecting. So if we have something like this, I want to get some color in here. Okay, let's say that we have 2 is big, right? The bases are people who use multiplier, it's a normal sized number. And I want to go up with a power on it. And then I want to do something else too. I want to have another base, a second base, as it were. And let's see how we can work with that. 3 is another base. And let's have that up here twice. And then let's say that there's multiplication going on between them. What does that mean? Well, we've got the base of 2 and the power of 4, which means I have several 2's. How many do I have? I have 4, but I don't have 2 plus 2 plus 2 plus 2. I have 2 times 2 times 2 times 2. So this is not 2 times 4. We already know how to do that. 2 times 4, they'd be the same size, maybe with parentheses or a dot between them. No, that's a smaller written 4. It's a bigger number as far as its capacity than the 2, but it's telling me I'm counting the 2's for you that are multiplied together, and there are 4 of them. So you write your 4 2's like that. And I'll put my black dot that'll represent multiplication. I'll start working on my 3's, where there's my first one, and here's my second one. And if you want to see what this thing makes, well, I'll show you what it makes. I'll just do this drawn out but quickly to show you what goes on here. 2 times 2 will be 4 times a 2 and a 2 and a 3 and a 3. And then 4 times 2 will be an 8 times a single 2 and a couple 3's. And then 2 times the 8 will get me 16 times a couple 3's. And then 16 times 3 will get me 48, still times a 3. And then I'll multiply that and I'll get 144. And that's what could happen if I wrote them all out. Well, we have a way to take care of this, which is when we have the order of operations, we tend to go with P and then space before E, then capital MD, and then space before AS. And some people pronounce it PEMDAS. You better know how to spell it, and you also need to know where the blanks are. But that's what we're going to use for order of operations. I've actually heard people say PPMDAS, but then that opens the door for people getting confused between this, which is for parentheses, and this is for exponents. Remember, the name exponents instead of powers would be really helpful for that. What's that saying we should do, right? These are the orders of operations. We're going to look at them more closely in a little while so that we don't have to do all that multiplying out one little bit at a time. What we'd like to do is get all 4 of the 2's together and get that number done. And if we do, if you look when all 4 of the 2's are together, there are no more 2's here when I've created the 16. And then that leaves behind for me to deal with 3 times 3, which I also happen to know is the number 9. And what's the easiest way, or maybe the most efficient way for us to go through doing this, is to go ahead and figure out what all the 2's make as a product. The product is what we get from multiplying. Get them to create one number for what they've created. And then do the same thing with the pair of 3's. This is not 3 times 2, this is 3 happening twice for multiplying. If you treat it as 3 times 2, you're saying, let me add a couple 3's, but we got a way to do that, right? Or if you want to say, let me multiply 2 times 4, we have a way to do that. This exponent, it's really important that it's smaller and elevated. So then that's saying my job here is to tell you how many of my base are present right here, getting multiplied together in this term. That's making a product, multiplying by that product, the whole thing still one term because there's no plus signs separating them. So this is what's going on when we have the base and the exponent. The result is the number that it makes after we finish doing out all the multiplication. But what happens is adding and subtracting, they're a little bit quicker than counting. They're a faster way to count. Then we get to multiply and divide. Multiplying is a quicker way to do the same kind of adding over and over, and dividing is the quick way to do the same kind of subtracting over and over. When we get to here and we want to do our multiplication faster because we keep multiplying by the same thing, instead of having to do it all out even though they're the same, we take advantage of the fact that the base is the same. We do exponents work. Actually, if you allow use of fractions, it can also do repeated division, but that's a little trickier to get into. And the all-powerful is the parentheses, which says I need to be a single number before you can start using me for something else. So this is where our order of operations comes in, and you've seen here that I didn't do anything in particular when I drew them all out to what they were representing to get my 144, because if you take 9 times 16, you will also get 144. But it might be quicker if I say, all the 2's make me 16, all my 3's make me 9. Let me do 16 times 9. And therefore, we're going to, instead of writing the exponents out and then doing multiplication, we're going to try and evaluate the exponents when we get that opportunity. Order and spacing are really important for order of operations. So you can't say, oh, I know those letters and I'll just put them in whatever order I want. No. A lot of people know that it's P, E, M, D, A, S. But a lot of times people will say, oh yeah, I learned it, it's this. That's not good. All right, it's not terrible. Right? There are worse things than knowing that. It's good that you have the letters in space, but some of these are clustered together. It should be P, then space, then E, then space, then MD, then space, because they have powers of like their importance or their priority. What we're going to do is we're going to take care of all these parentheses. Now, what do we do with parentheses? We do the work to get what the parentheses contain down to a single number. Within those parentheses, we have to still honor the order of other operations. But we do order of operations inside the parentheses and get them down to a single number. There is distributing that you can sometimes use, and sometimes you have to, because you have what we call terms that are not like, and they have this value that they need to distribute. But if they're numbers, they're all inherently like terms, and they're allowed to become a single number, and that's what we're trying to do. So get the parentheses done, get them down to be a single number before you advance to more work. This is exponents. After you've taken care of getting those parentheses done, go ahead and look around and see if you have any exponents. Because the exponent is a powerful way to do your multiplying, so powerful that we should do it before we get into our regular old multiplying. I did some work this summer listening to a podcast and hearing how they do things in Great Britain, and this is what you should do for sure, is you should put together your multiply and divide. And you should multiply and divide from left to right. Okay, you go across, they are not separate from each other. This is not P, then E, then M, then D, then A, then S. It's P, done with the parentheses, onward to the exponents, they get their own category. Multiply and divide are clustered together. From left to right, you can do multiply and divide, and that's great. And if you do that, as you encounter any multiplying and dividing, you deal with it, you will be fine. But some people inadvertently think they should do all the multiplying before they go back and do any dividing. That can lead to trouble. And in fact, what I discovered this summer was that if you do the dividing before you do the multiplying, it actually works out fine every time. It may create some fractions you have to deal with, but it gets the right answer. Because if you do the dividing before you do the multiplying, it will not throw you out of sequence for what you need to do. But multiply and divide, you want to treat those as their group. Once all your multiplying and dividing is left, all that's left is adding and subtracting. If you do what I've already been showing in earlier classes, you won't actually have any subtracting, because you'll have put in blue plus signs. They may not be blue, but plus signs when you saw minus to create addition of a term that begins with a dash for a negative sign, right? You'll go ahead and work on that. But if you've turned it all into subtraction, now all you'll have there is PEMDA instead of PEMDAS, because there will be no subtraction, and you don't have to worry about getting them out of order, about going from left to right, because addition, if it's all addition, you can do it in any order. So I'll recommend that you keep thinking about putting in those plus signs and creating a situation where the terms are free to move around as part of the sum. That does not happen with subtraction, but if you make an addition of terms that are negative, you have that available to you. Turns out that if you do the subtracting before the adding, it also works out flawlessly. But most people have learned it this way, as please excuse my dear Aunt Sally. It's not please excuse my dear Aunt Sally just flowing across the words. You gotta get the rhythm. Please excuse my dear, they're jammed together. Aunt Sally, they're jammed together. And remember, Aunt Sally might just be addition if you do that conversion that I have recommended for so long. So let's look at this simplest case of order of operations. 1 plus 2 times 3. Okay? If you grab a sort of checkbook calculator, it will get the wrong answer. Nothing wrong with checkbook calculators for doing adding, subtracting, multiplying, and dividing when you do them in the right order. You just ask them to complete those little operations. But if you rely on a calculator that's only designed to do those 4 functions, it may get this wrong, because it might think 1 plus 2 is 3, 3 times 3 is 9, and that's incorrect. So do check on your calculator and make sure that it gets the number it should, which is 7. Because order of operations says that we need to do this in the order that they come up from PEMDAS. So the order is not from left to right the way you might read English. It's going to be parentheses to one number, right? In the parentheses, you kind of, when it gets tough, you got to honor the other levels of what's going on. So if you got a lot going on in the parentheses, in there you got to honor all the others, exponents before you multiply and divide, before you add and subtract. Then exponents, evaluated to one number. So that as you move through this process, then you'll do your multiply and divide. Now, I do recommend that you consider doing dividing before multiplying, but if you do them as a group, it's multiply and divide. So I guess if I'm capitalizing the M, I should capitalize the D and divide. From left to right is the most common way people do it. Okay, but if you did the division first, it will never throw you into the wrong answer. If you just did if you wanted to do it one letter at a time, then this thing would have to be called PEDMSA, and then that would work perfectly. But then you got to go come up with your own sentence instead of "Please excuse my dear Aunt Sally." And I don't want to have everyone trying to learn that new, so I will support that. But yeah, doing the division before the multiplying, doing the subtraction before the adding, actually has some power. When all the multiplying is done, then you'll do add. And I'll put here and subtract, because the reason I'm doing that in parentheses is I believe that we should have turned the whole thing into a sum when we had subtraction. Insert the plus sign to turn it into a sum to get the mobility that we get from addition. But this would be from left to right. Of course, if you don't have any subtraction still hanging around, then you can do that. Or you can also change the order of that. And this is the order of operations. We've got to complete these as we get through the work. Now, there are a few things we need to know about order of operations that aren't just covered by PEMDAS. What happens when I see 1 plus 2 times 3, I take my 1 and I leave it alone because I need to do the multiplying before I can come back and do the adding. Because what should be happening here, the reason that's 7 and not 9, is there's only a single 1, but 2 times I have 3's. And so I have 7. That's not the same thing as this 1 plus 2 in parentheses now times 3. Because then order of operations says, well, let's get those parentheses down to one number. Absolutely, let's do that. Those parentheses represent a 3. This is not 33. There's 3 with no sign telling us what to do, means we must multiply 3 times 3. This will get us 9. So parentheses matter, okay? Sometimes the outcome will be the same whether you have parentheses or not. We're not here to try and memorize 1,000 different ways, 500 of which parentheses matter and 500 which they don't. We're trying to give the parentheses the opportunity to have an impact, and sometimes they won't, and when they don't, we'll just move on and keep going with the answer that gets generated. So we're not here to try to, like I said, memorize 500 times when parentheses do matter and 500 times when they don't. We want to just be ready to have them get a chance to be impactful. Let's go through some of these things. I'll put some up here for us. We've got 11-6 plus 4. Okay? Right out of the gate, I want you to know that order of operations is this. It's please, then excuse, then my dear, and then it's my Aunt Sally. And it's from left to right. So, looking at this, there's no parentheses, no exponents, no multiplying, no dividing. We get our AS, we're supposed to do this from left to right. Left to right would tell us to do 11 minus 6 and get 5 plus 4. and then go ahead and get 9. The mistake people make is sometimes they think that that all the adding should be done first, and they'll think it's 11 minus 10, which is incorrect. Adding and subtracting are equals. Now, the thing I've taught you in other classes, or at least I've given you an opportunity to work with, is this. When it says minus, convert it to plus dash 6, right? That's 11 plus negative 6. Now you might think, I'm done, it's 9, I got it. Well, the thing that's going on here is we have an 11 and a plus and a plus, and if I put the 4 here and then the negative 6 there, you can certainly see 15 plus negative 6 and get the 9. Or even if you don't move it, 11 plus negative 6, I call this stringing, but 11 plus negative 6, subtract and get the 5, strong on the positive like the old 11. Take the 5 and add the 4, okay, you got 9, and that's fine too, because you created plus. And in that case, if you make them all into plus, you can go from left to right and do the addition as they amount to their different values until you're done. But, very big problem, even if you've known PEMDAS before, if you misspell it, you might think it's 11 minus 10. So I wanted to put that in there, make sure we got that properly done, the answer that it should be. All right, I want to go with this now. Take down some of this. PEMDAS is representative of what we have here in our notes. I've kept the PEMDAS up there. I'm going to get some space for us to work with. All right. Next one I want to do is 3 parentheses 6 dash 2 plus sign and then 4. Order of operation. We go through. Anything in parentheses must be converted to a single number. And that's where I deal with this 6 minus 2 or 6 plus negative 2. So the 3 stays alone. 6 plus negative 2, subtract for 4, strong on the positive like the 6. So I get 3 parentheses 4. It's not 34. Do I see any exponents looking where they would be? No. Okay, multiply and divide? Sure. 3 times 4 is multiplication, so I'll take care of that. It's 12, and still leaves a plus 4. Now it leaves me now 12 plus 4, no division, any more multiplying or dividing, nope. I got adding or subtracting, this is straight adding, so I'm going to get 16. But as they get longer, there's more opportunities to have things get away from being from left to right. So don't say, oh, I just hope it works left to right and I'll get some of them correct. We need to be able to know the power of these operations. So here we have 3 power to 2 minus 4. That's not 6 minus 4. That's not 32 minus 4. That is a 3 happening twice. 3 times 3 is going to be 9 minus 4. I might do this and get myself 5 and be done. In that case, if I know how to do an exponent, so I don't make a 6 out of that, I will know that this makes 9 minus 4, and I'll say, okay, now I got 9 minus 4, and I got 5. See, this isn't so bad. You don't want to rely on the luck of having problems that work out without you knowing what you're doing as the way you're going to get these problems correct. So as we build through, we did see there were no parentheses, but we dealt with the exponent to get the number 9. We had no multiplying or dividing after that, and we saw that we had adding of negative 4 or 9 minus 4 to get that work done. Something that you need to know about this is keep fractions, numerators, and denominators separate, as though each was in parentheses. And if you treat it that way, you'll be okay. People do some funky stuff. If you've ever seen canceling, there's a lot of bad stuff people do because they love the power that they're given to cancel and make math shorter, quicker, and easier. But it's not a free access tool. And this approach of keeping the numerator separate from the denominator until we have a fraction, because it's like they are in parentheses, then we'll deal with the fraction it creates, and then later we'll look at specific opportunities we have to do things like canceling. But right now, 4-2 is in parentheses, followed by a 6, and then it sits over 3. Now, if you know how to cancel, there is an opportunity here, but I don't know if you can always tell the difference between those. So what I'm going to say is let's stick with the idea of what's the numerator equal to. Well, it's a 2 in the parentheses times 6. The bottom is still 3. 2 times 6 will get me 12 over 3, and then I can get 4 over 1 and get 4. And that's fine. Could you have gotten away with canceling the 6 and the 3 if you're aware of it? Yeah. But right now, let's get really strong foundational skills in keeping the numerator and denominator separated until they each have a number, and then we'll deal with them like that. So when you see a fraction, don't start crossing the fraction bar in these problems, but get each one of them evaluated, and then we'll see what opportunities present themselves when we have one number in the numerator, one number in the denominator. Okay, let's see. Now I want to take that one and make it a little bit more expansive, so we know what's coming on this. That's in parentheses, and then this. This has everything. It is in the numerator of the first term, parentheses around 4 minus 2, then a 6 behind it. In the denominator, we have a 3. Plus, beginning the next term, in parentheses, we have 5 minus 2, and then that pair of parentheses is raised to the power 2. What we need to do first is get the parentheses each down to a single value. 4 minus 2, 4 plus negative 2 will get you 2 inside the parentheses with the 6, and there's a 3. We've dealt with that already, so we're okay with where that might be going. Look at this other one, plus 5 minus 2 is actually the number 3. 5 plus negative 2, or 5 minus 2, and that's going to be to the power 2. As we move on to our next step, we shouldn't say, well, what can I do here, what can I do there? You're allowed to in some cases, but it's probably the best idea to look for any powers that we have there, right, any exponents. So we're going to let the 2 times 6 over 3 in the first term stay unfinished right now. Plus, we've got to do 3, not times 2, but 3 times the second 3, and get ourselves a total of 9 for that term. Now, we can go ahead. We've done the parentheses. We took care of the exponents where that 3 was to the second power or squared. We're going to look for any multiplying or dividing. So this time, 2 times 6 is going to happen. It's over 3 and plus 9. Don't do the plus 9 yet. 12 over 3 is going to make 4 over 1, or just 4 plus 9, and lucky 13 comes up as our answer. Because after we did the dividing, for our multiplying and dividing, all we had was a 4 plus 9 to do, which we did, and we got 13. So order of operations is going to go through doing these operations, first parentheses down to a single number, then any exponents and get them worked out to a single number. Then we'll go through and we'll do our multiplying and dividing until all multiplying and dividing has been absorbed and gotten, again, single numbers for us. And finally, we'll go back and take care of our adding and subtracting, which I might convert most of the time right into addition. It'll include some negative terms. All right, so a lot of times people want to quit on something like this. 3 square bracket 9 plus 3, parentheses around 6-4, close the parentheses, close the square bracket. This is what I was talking about earlier when I mentioned inside the parentheses, or in this case the square brackets, you have to get a single number, but while you're inside there you have to honor the order of operations. So this 3 is going to hang out for quite some time. We got our square bracket here. 9 plus 3, a lot of people think 9 plus 3, no matter where I see it, is a 12. That's not true. What's happening here is we're going to have to wait for the 9 plus and write the 3, because none of those get action right now. It's not time to be adding. It's time to deal with inside these parentheses 6 minus 4. So inside those parentheses you have 2. Now you might think it's time for 9 plus 3. If you do, you're incorrect, because we've taken care of that pair of parentheses, but these square brackets represent another containing pair of parentheses. They're not always parentheses, there's brackets, there's braces, but they have the job of saying, I get to be one number before you work with that 3. Further, inside these square brackets, we still have to honor the rest of the order of operations. So if we're only focusing on what's here, we don't do 9 plus 3, which is addition, until after we've looked for 3 times 2, which is multiplication. So the 3 is going nowhere right now, and the square brackets stick around. The 9 actually waits for 3 times 2 to do its job of becoming 15. So 3, outside the square brackets, 9 plus 6 is in the parentheses, which is why it's happening before we multiply. And 3 times 15 will close out with 45. Now I want to look at this one. It's a fraction. Doesn't look like a fraction yet. Still doesn't look like a fraction. Now it does. But up in the numerator of that fraction, we have 14 minus 2 times 3, and in the denominator, we have 7 minus 5. So, what we have is a numerator to get completed and a denominator to get completed, because it's like they're each in their own parentheses. Seven minus 5 in its parentheses, that's 2. 14 minus 2 times 3. Let's see, we're dealing with parentheses. I got the 2, we're dealing with these parentheses, and in there are no exponents. Any multiplying and dividing? Sure, 14 stays, while I get this to be minus 6, or 14 plus negative 6. Certainly we could. But you don't have to. If you can get that to 8, that's okay. So 14 plus negative 6 gets me an 8, and then the denominator is a 2. There's a 1 out here, which is why 1 times 2 gives me 2, no more parentheses. There's a 1 out here, which is why there's 14 minus 6 gets me an 8 and no more parentheses. Dividing by 2's, we'll get 4 over 1, and the answer here will be 4. A word about canceling. If you saw 14 minus 6 all over 2, you can't cancel there. If you've ever dealt with canceling before, and you think, I know what I'll do. No. Quick explanation with no writing. I don't want you to do canceling, but some people think, I will cancel the 2 with the 14, get 7 minus 6, and get 1. That's not 4. 4 is what the answer has to be. Maybe someone else will say, I'm going to cancel the 2 with the 6. I'm going to get 14 minus 3. I'll get 11. 11's not 4. The only answer can be 4 when it's fully done. You're not allowed to cancel the 2 and say, look, I'm cutting the 14 in half, we're good. Because in that case, you're only cutting the 14 in half and you're letting the 6 stay full. What we wound up doing was cutting the 14 in half and cutting the 6 in half. If you wanted to do that, there are ways to do it. But the whole numerator has to be done into one number. So we're going to do that. So don't rush ahead and try and cancel, because a lot of people love canceling so much that they do it crazily. I call it serial canceling when I teach courses that involve stuff like that. All right, 5 plus 3, square bracket, 10, round parenthesis, 3 times 7, minus 16, close the round parentheses, minus 30, close the square bracket, and I won't burden you with putting, a minus sign or something behind there. There's enough to learn here to get us going. 5 plus 3 doesn't always equal 8, right? 5 plus 3, if it's all you've got, will equal 8 all day long. But here, there's more going on by a long shot. So what I'm supposed to do is look for parentheses. And because I have parentheses inside parentheses, I should go to the smallest set of parentheses. That means the 5, the plus, the 3, the square bracket, the 10, all don't change right now. In those parentheses, I have 3 times 7 minus 16. 3 times 7 is multiplying, and that is subtraction, or also known as adding a negative. So I'm going to do the multiplying in there, and I'll get 21 minus 16. Skipping steps is something people always have some idea that they want to do, because they want the math to be over. But doing too much of that means you want the math to be over whether it's right or wrong, and then you wind up maybe doing poorly on the test and taking a whole class again. So now you've saved a few seconds on this problem, and you wound up spending a whole other semester trying to get it right. So I'm going to say, let's not skip steps. I don't mark it wrong if you skip a step and do it correctly, because your thinking is 100% solid. But if you start skipping steps and say, the answer's 7, I got nowhere to go for even trying to give you partial credit on that. 5 plus 3 still isn't always going to be 10. Let's see what's going on. That pair of parentheses needs to be done. So I will keep the 5, the plus, the 3, the square bracket at 10. In this, I do know 21 minus 16, I might have to do it out vertically and all that, but I can see that it's a 5. Those parentheses become a 5. Still in there is minus 30 before I close the square bracket. So now that pair of parentheses is done, I now need to take care of the square bracket pair of parentheses. Here's multiplying, here's subtracting. Looking at options, I must multiply before I come along and subtract. 5 plus 3 still didn't happen. But I multiply the 10 times 5 and get 50 minus 30. It's still not that square bracket a single number, so it's got to become 20. 5 plus 3 still didn't happen. The square brackets, when I do 50 minus 30 or 50 plus negative 30, those square brackets will make 20. Even if they're square brackets, it still means multiply. It's just a different form of looking at what parentheses do. And so this is 5 plus 3. By itself it would be 8, but we're not by ourselves. We've got to decide, are we going to add 5 plus 3, what we're doing adding? Or are we going to do 3 times 20, which is multiplying? Multiplying comes first. We're not seeing any more parentheses needing to be done or exponents, but there is multiplying. So that creates a 5 plus 3 times 20 is now allowed to happen and make 60 before we get, the last step is to add 5 and 60 to get 65. By having me write out all those steps, you can see what the next step I did was. Is it absolutely essential that I see 50 minus 30 when you can see that that made 50 minus 30 and you could get right to there? No, but should you go from here to 65? Also no. So order of operations are necessary because certain operations are stronger, more capable of getting jobs done, and that's why parentheses get so much attention, because they're like, you gotta get me, I get your first attention, you gotta get me a number. Exponents like, I'm so strong at multiplying, don't bother with that little multiplication, the old school multiplication, because I'm a stronger form of multiplication. You gotta deal with that. Multiplication, division are stronger than adding and subtracting. They gotta get their due. They have to get taken care of, and that's order of operations for you. So, I want to take a look at something about decimals in this, and then we're going to move in to the second part of 5b. What we want to do, which is greater among decimals? How do I do that? Number one, set them on the number line. That's if they're clearly different. Okay. If the number line's vertical, the higher one is greater, and that's easier. The lower one is the less one, and that's the one that you would point the arrow at. Okay. If they're close, line up the decimals and insert ending zeros as needed. So when you have a negative and a positive, it'll take care of itself. When they're both positive, you'll probably feel out the way that you're pretty sure, oh, 7 is greater than 4. But when you get into the negatives, it really helps to have them on the number line, because you're like, oh, look, that's worse. Worse is lower on the vertical number line. More to the left on a horizontal number line, but worse is lower. And you'll know which is better, which is worse, which is greater, kind of thing. All right. I didn't have any of them in our order of operations, but another thing that I want to do is I want to come back and mention what square roots do in just a short while. I want to look at my next sheet. Because I want to look at when we have 2.34 and 2.345. These are these which is greater kind of questions. 7.54, 7.5397, and negative 15.62 and 1.562. Now these are close on the number line, so how do I do that? I got my 2.34, I'm going to grab a green marker for inserting zeros, and I have my 2.345. The decimals are lined up, and look when the tie gets broken. Okay, they're tied in the units, they're tied in the tenths, they're tied in the hundredths. The tie is broken 45 is greater than 40. The putting in of the 0 there helps me see that 45 is bigger than 0, or even that 5 is bigger than 0. You want to point to the lesser one, so you want the one with the 0 getting pointed at, even if the 0 is not there. This is line up the decimals and insert the ending 0. Zeros can go to the left or to the right to make sure you have full columns for comparison. This one, 7.54. And then this one goes 7.5397. If you put the zeros on the end there to fill it out, you can see that they're tied with 7s, tied with 5s. It breaks at the 4. The one that goes 7.54 is greater, you point at the other one. This is saying 2.34 is less than 2.345. This one is saying 7.54 is greater than 7.5397. Even though that 97 might eventually round up in a lot of cases, there's no denying that 400 is greater than 397. So you gotta say, if you're breaking, there's a tie getting broken somewhere, you can see that. But the whole time, see, those would be tough to do on a number line. This one, when I set up my number line vertically, here's 0, I will put my negative 15.62 down below 0, and I will put my 1.562 above 0. And even though that one's larger than 15, because it's negative, that's the bad one, that's the good one, point at the bad one. And as far as a bank account balance goes, you go like that. And this is how we determine which is greater among decimals. When they're close, you line them up, right? If there's signs involved, you put them on the number line. And if you have something like this, negative 13 and negative 4, put them on the number line. 0 is here, negative 13 is down here, negative 4 is not so far down. The one that's worse is the negative 13 when you do that. That's the vertical number lines. Now most people would say, well, can't we do that on a horizontal number line? Oh, absolutely. But I don't know if it's as clear to most people that when I put my 0 here and my 1.562, and then if you're trying to draw out anything to scale, you might see the negative 15.62 out here. Sure. But I have had people have more success, I believe, with the vertical number line. So that when I were to say, oh, negative 13 is the first one I have, that's out here. Where's the negative 4? It's not as far out there. Negative 13 is worse as a bank balance, and that makes it less. Now about the square root. The square root is very similar in its function of its overall job to absolute value. What? It's not that square root and absolute value do the same job, it's that they're from the same family. A square root sign is a special kind of parenthesis. An absolute value sign is a special kind of parenthesis. What they need to do is have you get the number that they offer you before you can proceed. So treat a square root sign as a special type of parenthesis. That means it gets dealt with when it's time to deal with parentheses. The square root sign asks, what two identical numbers are used to multiply to get here? That's what it's asking, which is weird. And only certain numbers have rational square roots. It's hard to get down to all what they are. But what I'm going to do is, this is the square root sign. It looks like division because in a way it is division, but it's not saying divide by a number I'm going to put out front. It's saying cut me into two equal pieces with multipliers. So I'll put some up here. Weird numbers, right? Two numbers that are the same. Not two numbers. Not like 1 and 25 or 10 and 2.5. Two integers that are the same. They both have to be the same. What times itself gets me to 25 is 5. How about 81? 81 is 3 times 27. You may or may not know that. But what's important to know about 81 when you come to the square root is that it's a pair of nines. A pair of multiplied nines. It's not a pair of, eights. This is not eights. This guy, 4 times 4 to get 16. Square root means that you want to decide how big is the number that multiplies by itself to get me here. And then when you're done with assessing the square root, you put only that number there. It's not 16 anymore. I'm going to tell you something that goes on in bigger levels of math. It's actually half the power of 16. Powers are used for multiplying. So instead of having the full 16, you only have half the power of 16. I need 2 of them to get there. Give me the 4. I need 2 things to get me to 49. Each one's a 7. So this is what's going on with square roots. They are special numbers. So if you face something like this, the square root of 27 minus 11 plus 5 times 3 minus the square root of 4, what we should be doing is saying that's a pair of parentheses. Let me get that down to the square root of 16. Plus 5, here's parentheses, so let me work on that. But wait, there's more. 3 minus the square root of 4. What times itself? Now 4 is kind of funky because 2 shows up all the time. 2 plus 2, 2 times 2, 2 to the power 2, but okay. A pair of 2's will make you get multiplication to 4. Now, this is a square root, so that is still needing to be done. Right, we got 16 as the only number in it, but what is it that I need 2 of these multiplied to make 16? That's a 4. Plus the 5, this is a pair of parentheses that gets me 1. Okay, now, watch this. 4 plus 5 times 1 is 5, and that's 9. All right, ready? What if the whole time it was like this? You did great to get here, right? What if it was? You would have done exactly what you did, and you're sitting in parentheses, and now you need to finish it. Ideas? Don't tell me 4.5. 2 numbers. What I like to do is do this so that I say, all right, don't give me 1 and 9 because they have to be the same. What are those? 3's. And that's what order of operations has us doing. Just treat the parentheses as, treat a square root sign as a special pair of parentheses. It's a tricky one because you got to do work at the end, but that's what it is. It's something that needs your attention to get it a single number. And that's why I threw the green square root on only at the end. Okay, so we're going to continue with homework 5. With lesson 5. What we want to